everyone, thank you for watching today. This is lecture 2 to make up for the fact that the in-class lecture lacked volume because of a technical difficulty with the microphone. The battery pack was dead. Now that's fixed, and this is to make up for it. So you're welcome to watch this on YouTube as well. The topics for today are going to be properties of functions, basically introducing functions, and the second half will be quadratic functions, basically parabolas. So let's actually talk about what a function actually is. A function is a rule that assigns to each element in a set A exactly one element in a set B. So a function, in effect, takes one input from the set A. Let's actually make that clear that A is the set of inputs, and B is the set of outputs. And the rules say, the definition of a function says that one input, one output. And this can be written with this arrow notation, f from A to B. This is read f as a function from A to B. From, because this one actually maps inputs in the set A, and to B because the outputs actually originate in the set B. So f takes one input from the set A and outputs exactly one output from the set B. So this function is in fact a machine or a formula or any other way you want to present the rule, and this rule takes one input from set A and maps it to exactly one output from the set B. The pool of possible inputs is called the domain. That's going to be the A. The domain is basically what I am plugging into the function to actually test its outputs. So anything that's plug-inable, so to speak, into the function is going to be the domain. That's the domain. And the pool of possible outputs is called the range, which is contained in the set B but may not be all of it. I just want to stress this, that A cannot have orphans, the domain cannot have orphans, while the set B just has to be large enough to cover the outputs. B can have orphans. There may be elements in the set B that do not get covered as an output. Now, if the function f assigns to the element A in the domain the element B in the range, then we write f of A equals B. This means that when you plug in A, the function spits out the output B. So f of A is equal to B. F of A equals B, meaning f sends little a to little b. When you provide it little a, it will provide little b. And like we have stated in this course, A and B will always be subsets of the real numbers. Now, people have asked me about this. What do I mean by real numbers? By real numbers, I mean nothing more than all the numbers you know of that you can plug into a calculator. So integers, 1, 2, 3, negative integers, -1, -2, -3, yada yada, and all the fractions in between, 1.5, 1.33, third, -1/10, -5/2, as well as some special numbers, one of which you already know, that's pi. For instance, pi is just one of those special numbers, but it's still a real number. So in this class, you will be dealing with the numbers that you can actually plug into an ordinary calculator. We will not be talking about special imaginary numbers that extend this. So no need to worry about that. When I say real numbers, I mean just this number line that goes from all the way to far left to all the way to far right. That's what we mean by real numbers, with a zero punctuating it halfway in between. So real numbers. Okay, beautiful. Now let's actually talk a bit about the mapping and range analysis. Let's actually look at our first example of a function. This one maps inputs from set A, being 1, 2, 3, maps them into the outputs in the set 4, 5, and 6. Let's actually observe a few things going on here. What is f of 1? 1 gets mapped to 4. 1 gets mapped to 4. Follow the arrow, and the end of the arrow is at 4. Good. Now, what about 2? Map it all the way to the end, and what do you get? You get 4 still. Good. Map this all the way to the end, and what do you get? You get, from 3, you get to 5. So, two things are going on here. There are no orphans, of course, in the set A. The domain must not have orphans. Every input in the set A, that's this one, has to have exactly one output. That is the case indeed here. No two elements in A are collapsing or end up at the same sorry, no one element in the set A is actually diverging and going into two elements. One maps exclusively to 4, 2 maps exclusively to 4, and 3 maps exclusively to 5. Now, let me point your attention to something interesting here. Let's see. There is also one thing I would like for you to note. Some people might say this is not a function because 1 and 2 get mapped to 4. That is not forbidden for a function. One input cannot have multiple outputs, but two inputs can map to the same output. That's fine. We have already seen this, in fact. Think of a constant function. The function that, regardless of what you plug into it, spits out the same number, for instance, 0, that is technically a legitimate function, even though it's not very interesting. In this case, the fact that 1 and 2 map to the same output 4 does not detract from this being a function. One more thing I want to point your attention to is that 6 in the set B is an orphan. That's fine. We've said that B is actually has to be large enough to actually cover the entire range. In this case, the range is 4 and 5. So let's write this in curly braces. That's going to be 4 and 5. Literally put the two elements in the range into kind of this grab bag of elements. In this case, 4 and 5 are the range because they're the only outputs that get this is mapped into. So 4 and 5. Good. Now, this is what it means to have a domain in a range, and in this case, B is larger than the range. B has 6, which is an orphan. B is not an output. There is no element in the set A that gets mapped to element 6 in the set B. So B can be larger, that's absolutely fine. Now, let's actually take a look at the bottom one. Determine whether the relation illustrated below represents a valid function mapping elements from set A to set B. Explain your reasoning. Okay. Well, unlike the previous example, here there seems to be a problem. The element 1 in the set A, that, if we follow the arrow all the way through, there are two arrows emanating from it, and they lead to two distinct elements. So 1 gets mapped to 4 and 5 at the same time. So 1 is mapped to 4 and 5 at the same time. This is forbidden. This is forbidden. Not a function. Good. So this is certainly not a function because the input 1 gets mapped to two simultaneous outputs, 4 and 5. No good, not a function. Okay. Functions can be described in several ways. Equations, that's one we'll be seeing plenty of in class. What I mean by this is formulas, aka formulas. Something that literally you can take a formula, plug into it, and the formula provides you with the output. Graphs, we'll also be paying attention to that. In fact, a section of the textbook covers graphs and graphing functions. Table, this is less common, but nonetheless good to know for illustrative purposes. Diagrams, we have already seen these examples with the circular diagrams. And verbal descriptions, which again we may see of when we deal with word problems in a few weeks, but the two most common forms of functions we will see in this class are equations and graphs. Let's actually, it's often helpful to describe a function in multiple ways. So even if you know the function's formula, it's still good to know the graph, because sometimes it's easier to describe things graphically than verbally. And it's also good to know things verbally sometimes, even when you have a formula that's ready to use in a calculator. Now, please let me actually point your attention to two conventions. When an equation involves x and y describing a function, x is always the independent variable, meaning x is what you plug in. X is your responsibility. X is something that's collected from the user. Imagine a function is kind of a machine or a computer terminal, and you're the user. You, as the user, will actually provide the computer or the formula with x, and then the y is the function's responsibility. That's the dependent. That's the output. You provide your computer with x, and your computer shoots out or spits out y as an output. We provide the function x, and it provides the function, and it provides the value y for us. Okay, that's just a matter of convention. If a function is given by an equation and its domain is not explicitly specified, It's taken to be the largest possible set. So when I give you a floating equation that's not attached to anything or any background context, and you want to figure out the domain, the way you want to do that is you want to take the largest possible set of numbers that you can actually plug into the function and it won't go haywire, or you won't break one of the cardinal rules of mathematics. So far, we have only seen two cardinal rules, or I will introduce you to two cardinal rules in the class that you're probably already familiar with. Number one is you must not divide by zero. If there is ever a number that will cause you to divide by zero, that is automatically excluded from the domain of any function. You must not actually plug in a number that results in division by zero. Good. On the other hand, you must remember that we do not take negative square roots of negative numbers in this class. So for instance, let me point your attention to this. Square root of 4, for instance, is 2, because 2 times 2 is 4. And square root of negative 4 does not exist in this class. Not in this course. There's also another thing. If you're actually doing functions in a physical context where the variable x stands for something physically significant, then you also have to pay attention that it physically makes sense. For instance, if x is the amount of food in a certain problem, it makes no sense to talk about -1 kilogram or -1 pound of food, or -3 inches of length, or -3 cubic inches of area. So far we have seen two cardinal rules of math in terms of arithmetic. Never divide by zero, never take the square root of a negative number. And at the same time, if your variable means something physical like area, weight, length, height, things of that sort, be careful that it does make sense. For instance, it doesn't make sense to talk about -3 kilograms of food in a supply chain, for instance, or -5 pounds of butter to make our cupcakes from the previous lecture. By definitions, two functions are equal if they have the same domain, and if for every little a and big A, f of a equals g of a. What do I mean by this? Two functions are equal if they're the same machine, if they're the same formula. When you provide two functions the same number, little a, they will spit out the same output, whatever it's called, little b, for instance. They have to have equality. The formulas have to overlap, and in addition to this, the domains have to overlap. So in addition to this, it's not enough to have two functions spit out the same thing. They also must have the same domain. We can't have functions that are equal but don't have the same domain. For instance, one function you can plug 0 into it and the other not. We'll see more examples of this when we do limits. But for the time being, this is what I wanted to discuss in terms of equality of functions. Now let's talk a bit about this example. Determine the domain and the corresponding range for each of the following functions. Okay, let's talk about a. What am I allowed to plug into a? Well, it's x squared. Any old number I can take into a calculator and multiply it by itself. Negative, fraction, 0, anything at all. So nothing is preventing me here from plugging in any old thing I want. So can plug in anything. Domain is all real numbers. When I say all real numbers, I mean literally anything you can plug into a calculator. So even if you omit the word real in this class, it doesn't matter, so I'll put it in parentheses, real numbers. That just means anything you're already familiar with from school arithmetic. That's the domain. That's what I'm allowed to plug in. What is this function capable of producing or spitting out, to be vulgar, as an output? Well, you'll recall that x squared is always going to be non-negative. That's the beauty of even powers. For instance, example, -1 squared is actually going to be 1. So this thing seems to be able to spit out anything positive, and only positive things. It can never be negative in this class. Even powers will always be oblivious to the minus sign and will always cancel it. So in effect, what I'm trying to say is that it can spit out anything positive, and it can also spit out something 0. 0 squared is equal to 0. Lo and behold, I was able to produce something 0. So the range is all non-negative. When we say non-negative, what I mean by this is all the positives and 0. This is different from the word positive. Positive means something that's positive and not zero. Non-negative means positive or zero. Non-negative numbers. Okay. Let's move on to example B. This is a line that we have already seen from the previous lecture, a linear function. F of x equals negative 2x plus 3. This is a line. Now, what about this line? What can we plug into this line? There is no danger of division by 0 or taking a square root of something negative. So again, domain can plug in anything. Domain is everything, no restriction. Let me ask you a little something now. What about the range? Well, if you actually look at this function, it can produce anything. I can plug in a humongous number, for instance, a million, and I'll get negative 2 million plus 3, which is something negative. So looking at it, it seems like I can produce any negative number I want. I can actually plug in something negative and get something positive. In fact, if you draw the graph of this little function, you will find that it is a slanted line along the lines of this. This is what it looks like. A slanted line with a negative slope. Let me just remind you, the coefficient of x is negative 2, so it's a negative slope. Good. So in effect, this is the domain is everything, and it seems like the function can actually spit out anything. Any old y you want, you can find an appropriate x, plug in, and it will produce y. You think, do this experiment on your own, or look at the graph. It covers all of the y-axis. So, range is also everything. What about the example in C, 1 over x? Well, you can plug in anything, but there is a risk of dividing by 0, so the only number that gets excluded is x is not 0. Domain, x is not 0. In addition to this, let me point your attention to the fact that 1 over x can be positive. If you plug in something positive, you will have something positive because numerator and denominator are positive means something positive. If you plug in something negative, you'll get something negative. Again, positive 1 divided by negative will be negative. You will never have 0. Why? Because for a fraction to be 0, the numerator must be 0. Unfortunately, in this case, the numerator is 1. Well, not unfortunately, I should have been more objective. But the numerator in this case is not 0. It's never going to be 0. It's always going to stay 1. So the range is always going to be non-zero. So range, everything but 0. But 0. Good. This is beautiful. What about D? Well, here we have the square root function. As we have said, the one cardinal rule to pay attention to in this case is that we must not take a square root of a negative number. So, in other words, let me point your attention to the fact that since the function is entirely a square root, the domain must be only non-negative numbers. Domain x is greater than or equal to 0. Let me remind you, we can't take the square root of 0. If I can remind you that it's the square root of 0 is 0. The square root of a number is the number that when you multiply it by itself, you recover what's under the square root. Just to give you a few examples, square root of 1 is 1. Square root of 4 is 2, because 2 times 2 is 4. Square root of 9 is 3, because 3 times 3 is 9. And the domain is x is greater than or equal to 0. And as a matter of fact, not only is the domain all non-negative numbers, but so is the range. In this class, we take the square root to be positive. So notice 1 here, 2, 3. So it can only be all positive numbers. Range, or all non-negative numbers, because we also have 0. We've already said this, so apologies for omitting that. So range, all non-negatives. In fact, if you want to actually write it down, you can actually say for range, for x, it's for the domain it's x, but for range it's y is greater than or equal to 0. Now for the domain here, for the range here, everything but 0, so we can say y is not 0, does not equal 0, and that's lovely. And in the case of this one, it's everything, so we've already stated that. And for the first one, the range is all non-negative numbers, so y is greater than or equal to 0. Awesome. Okay. Now, let's actually take a look at the next example. Which of the following represent functions and which do not? Well, for the first one, actually, it's not a function, and let me show you why. If you plug in, for instance, x equals 0, which is legal, there's no calamity caused by this, no division by 0 or no root of a negative number. Plug in and you get 0 squared plus y squared is equal to 25. 0 squared is 0. 0 times anything, including itself, is 0. You get y squared equals 25. Let me point your attention to something, that when you take y squared equals 25, remember that the whole point of an even power is that it's oblivious to the minus sign. So we got y equals 5 or y equals negative 5. We got two possibilities, y equals 5 and y equals negative 5. Because, in parentheses, 5 squared is 25, and negative 5 squared is equal to 25. Good. And this is not a function, because for 1x, x equals 0, we got two y's. So 1x, sorry, not 10, 1x has two different y values. So this is not a function. Whoops, let me just remove this. Let me underline it just so it doesn't interfere with the one below it. This is not a function. Okay, what about this one below, y equals square root of 25 minus x squared? This is indeed a function. It does have a specific domain, which you can think about in a bit, or plug into Desmos and see what it gives you. But insofar as this function, this formula, this does actually represent a function. Plug in any legal x, and it can only spit out one y. Because in this case, we actually have only a square root, which we know unambiguously to be positive. So this is a function. This is a function. Good. Each x in the domain gets one y exactly. Good. Let's take a look at this next one. This is given to us in the form of a table. Now it seems like for x equals negative 2 we get 3 as the output. For the input of negative 1 we get 3. For input 0 we get 4, and for input 1 we get 4. This is indeed a function. Looking at this, inspecting it visually will reveal that for every possible input, we only have one possible output. So, one input, x, one output, y. So, a function. Good. This is a function. Let me just highlight this from the previous example. It's a good convention to, it's a good practice to put your final answer in a box. Not necessary, but just good practice. Now let's take a look at this function. Something catches our eye here. The input 3 has two simultaneous outputs. 3 gets mapped to negative 2 and negative 1. 4 gets mapped to 0 and 1. So, not a function. Not a function. Take your pick. 3 is mapped to 2 outputs, and so is 4. 3 gets negative 2 and negative 1, no good, and 4 gets mapped to 0 and 1. No good. So just take a look at these two little blocks, and each block is enough to violate the cardinal rule of this being a function. Okay, so far so good. Let's move on to something called a piecewise function, and examples of this we have already seen actually. So when we talk about a piecewise function, that can be defined by multiple formulas. So for instance, we have seen linear functions which are defined by, so for instance, f of x equals mx plus b. That's just one formula. A function can be defined by multiple formulas. This specific formula for mx plus b says, regardless of what input you plug in, x, always use this formula to figure out f of x. So, in the case of a piecewise function, we actually make a distinction. It's kind of like a table. We use multiple formulas to define the function, and each formula is invoked depending on the type of input you provided. For example, we have already seen an example with this, which is the absolute value function. The absolute value function is a piecewise function, because if you provide it with a non-negative number, its job is easy. It'll just spit out the same thing. Reminder, for instance, abs of 0 is 0. Abs of 1 is 1. Abs of 2 is 2. It just spits out the same number. That's the top branch. On the other hand, for the bottom branch, if you want to provide it with a negative number, negative 1 in absolute value is 1. How do we go from a negative number to its positive counterpart? Multiply by negative 1, or add a minus, because minus minus makes a plus. So this is 1. Abs of negative 2 is 2. Abs of negative 3 is 3, and so forth. So this is the bottom branch. To go from a negative number to a positive counterpart and for the function to do its job, it will actually have to multiply this by a minus. Okay? Now, we have already established how to check whether a function is whether an equation is a function, or a formula is a function, or whether a table or a diagram is a function. The only question remains, is there some kind of quick and easy and convenient test that we can look at, such that when we actually take a look at a graph, we can tell whether or not the graph is a function? This is called the vertical line test. So if every vertical line intersects a graph in no more than one point, then the graph is the graph of a function. This is called the vertical line test. So for instance, take the graph on the left. Any vertical line that you use to skewer your graph is going to hit the graph in exactly one position and no more. That is a function. On the other hand, if I were to take, for instance, in this case, the red one, and actually do this, we can see that for this vertical line, it actually gets mapped to multiple values. It skewers the graph in more than one position. Not a function. Not a function. And this one, on the other hand, is a function. Good. So, what I'm trying to say here is that, remember, for each specific input, there must be exactly one output. Graphically, this is the vertical line test. If you take a look at the graph on the left, take any x and look up the y. How do you look up the corresponding y to a specific x? Take your x and climb up vertically or down, depending on whether the graph is positive or negative. If you only hit the graph once, congratulations, that's a function. If you hit it multiple times, like on the right, then that's not a function. As we can see on the right, you can see that this little guy right here, this little guy gets mapped to multiple y values here, 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 and here. That's why the vertical line actually fails. It skewers the vertical line test actually fails. It skewers the graph in multiple positions. Now, let's actually talk a bit about even and odd functions. A function is even if f of negative x is equal to f of x for every x in its domain. What do I mean by this? It's oblivious to the minus sign. It doesn't care if you provided a positive number or a negative number. So it does not care. So even functions do not care about sign of input. On the other hand, for the odd functions, what you see happening is kind of the opposite effect. It does care about the sign of the input, and it will take the minus sign right here and transfer it to the front. So f of negative x, take this negative x in green, yank it outside, and you will get that it's negative f of x. So the minus sign gets yanked or transferred outside. Graphically, the graph of an even function is symmetric about the y-axis. I'll show you an example in a bit. And the graph of an odd function is symmetric about the origin, the 0, 0 point. The origin is 0, 0. Okay. Can you think of an even function? Okay, let's see. Can we think of an even function? Yes. F of x equals x squared. Why is that? What is f of negative x? It's equal to negative x in parentheses squared. That's x squared. The whole point of 2 and other even powers is that they're actually oblivious to the minus sign. So f of negative x equals f of x. So even powers, not just 2 by the way, even powers are even functions. Good. Can you think of an odd function? Well, let's try our luck with odd powers. F of x equals x to the power of 1, which is just x. F of negative x is just going to be negative f negative x. And what is negative x? Can you agree that f of x is equal to x? So this is negative f of x. Take this, and you will find that f of negative x is equal to negative f of x. Good. Odd powers, that's not just one. Odd powers are odd functions. Let me show you the graph, what these graphs look like. For instance, this one, we will get to this in a moment when we talk about parabolas, or in the second half, I should say, not quite a moment. So for this one, it's actually the graph of x squared is actually going to look like this. Sorry, x and y. It is actually going to look like this. Good. What about this one? This one, the even function, is symmetric about the y-axis. The y is kind of a perfect mirror. What about the odd function? Go like this, and you will see that it's symmetric about the origin 0, 0 like this. Just something good to know. As long as you're able to work with the definition, you're fine. Okay. Let's see. Can we think of a function that is neither even nor odd? Yes. F of x, let's take a hodgepodge of an even power and an odd power, like this. Take f of 1, and what do you get? 1 squared plus 1 to the power of 1. 1 to the power of anything is going to stay 1, so it's 1 plus 1, and that is 2. What is f of negative 1? It's going to be negative 1 squared plus negative 1, and that's going to amount to what? 1 minus 1, which is 0. Lo and behold, if this were an even function, then we would have had f of negative 1 equals f of 1. Not. Good. If this were an odd function, we would have had f of negative 1 equals negative f of 1. Unfortunately, that's also not the case. 0 is certainly not equal to negative 2, so that's not the case. Here is a function that is neither. If you want to find a function that is both, apparently, there is a function that is both even and odd. And let me point your attention to this. It is the function f of x equals 0. Why is that? F of negative x is going to stay 0. This function is always going to spit out 0 regardless of what you plug into it. Good. As it happens, 0 equals 0. So f of negative x equals f of x. That's even. And 0 equals negative 0. So f of negative x equals negative f of x. So it's also odd. Both are true for this function. This is the only true function that is actually both even and odd that we'll encounter in this class. Okay. This example is not so important, and we'll save that for when we go to limits. And this one is just a bit of extra practice on your own. It's actually really easy, and you saw similar examples on homework. So if you have any questions, and to keep in harmony with the lecture, I think I'll stop here, and we'll move on to the second half to deal with quadratic functions. Thank you. Hi, everyone. So this is the second half, quadratic functions, translations, and reflections. A quadratic function is basically this type of function. F of x equals ax squared plus bx plus c. This is what we mean by a quadratic function, where a is not 0. Because if a were 0, you would just have bx plus c, which is a linear function, not a quad function. So in order for you to have a quad function, you would need f of x equals a, not 0, times x squared plus bx plus c. Example, f of x equals x squared plus 2x plus 5. F of x equals negative x squared minus 3x minus 11, yada, 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 things of that sort. Just as long as this thing does not disappear, it does not get multiplied by a 0. This is the standard form or general form of a quadratic function. This is what we called standard form. There is another form that we will soon see, but that is indeed the standard form. Why is it standard? Just the default, I guess. And it's the easiest to actually write down, not necessarily the easiest one to deal with. We can always do a process called completing the square, as you saw in your worksheets, and that is in fact, that gets you the vertex form. This is what you would call the vertex form. Vertex form. And let me just point your attention to something, that this A and this A are one and the same. This A and this A are the same A, so that's not a coincidence. The H and the K are different from the A, B, and C, but the A in vertex form and the A in standard form are one and the same. Now, the graph of a quad function is a parabola, and the graph of a parabola can take on two shapes. Either what you would call smiling or frowning, depending on the leading coefficient, the A, basically the number that gets multiplied by x squared. So if A is positive, the parabola opens upward. It's happy, so it's smiling. If, on the other hand, the leading coefficient A is negative, then the parabola is frowning, sad. So think of it kind of as a smiley face and a frowny face, depending on whether or not A is positive or negative. If A is positive, your parabola is happy, so it's smiling. If the lead coefficient is negative, your parabola is sad, so it's frowning. Now, the function f of x equals ax squared plus bx plus c may or may not have zeros or roots. What do I mean by this? When you find the x-intercept, or when you attempt to find the x-intercept, you set this equal to 0. So it turns out that this type of equation can have two roots, one root, or no roots, depending on what the quad formula actually says. Let me remind you of the quad formula. The quad formula is this: x equals negative b plus or minus square root of b squared minus 4ac divided by 2a. That is indeed the quad formula right here. This is used to solve, ax squared plus bx plus c equals 0. Good. Now people will logically talk about two things, both of which are justified. First of all, we're dividing by 2a. Number one cardinal rule of arithmetic: you must never divide by 0. But lo and behold, we've assumed that a is not 0, so that takes care of this. The other thing that's left is we have a square root. We have a square root of b squared minus 4ac, this one. This thing under the square root. This is called the discriminant because it allows us to discriminate between the three possible cases that dictate the behavior of the roots of the equation. So this thing can actually be positive, in which case we have a plus or minus, meaning we have two distinct roots. That's if the thing under the square root, the discriminant, is actually positive. What about if it's 0? Well, in this case, you would have plus or minus 0. Plus or minus 0 is still 0. 0 multiplied by anything is going to stay 0. So we have just one root, or one double root, basically one distinct root. One distinct root. Good. What about if the discriminant is actually negative? Well, if the discriminant is negative, we cannot take the square root of a negative number in this class. We have already established that. There is no such thing as a square root of negative 1 or a square root of negative 4. Lo and behold, what do we mean by this? We must not take the square root of a negative number. That just means that no real zeros. No zeros as far as this class is concerned. Okay. If ax squared plus bx plus c actually factors easily into two linear functions, we'll talk about this just now, then it may be easier to find the zeros by factoring instead of using the quad formula. If you would prefer to use the quad formula, you're totally at liberty to do so. In fact, the quad formula is what you would call the bulletproof approach. No matter if the numbers are lovely or not, the quad formula will get you to where you want to be. Let me actually show you with this example. Recall this identity from high school algebra. X plus a times x plus b is actually equal to x squared plus a plus bx plus a times b. So we have x squared multiplied x squared on its own like this, plus a plus bx plus a plus b. A times b, sorry. So if we actually take a look at this, let's actually ask ourselves, let's match the x squared and the x squared here match. Now let's ask ourselves, what about the 3x and the a plus b here? We want to find a plus b such that their sum is 3. And if we actually take a look at a times b, you want them to be equal to 2. So a times b is 2. What two numbers can you give me that multiply to 2 and sum to 3? If we can actually try our luck with simple numbers, we can actually get 2 and 1. 2 times 1 is 2, and 2 plus 1 is 3. So x plus 2 times x plus 1. Beautiful. That's how you factor this. This becomes this. Or let me use a different color just so it's not too cluttered. This is equal to this. They are equal. Good. Now, let's take a look at the next one, x squared minus 4. Recall this identity from high school algebra. X plus a times x minus a is equal to x squared minus a squared. What number do you know that you can square and get 4? Well, that's 2. 2 squared is 4. So this thing factors to x plus 2 times x minus 2. Okay. What about this thing? Well, what two numbers can you give me that when you multiply them you get 9, and when you add them up you get negative 6? Well, why not take negative 3 and negative 3? So you will get x minus 3 times x minus 3. That's how we factor that. Let me point your attention to something, that negative 3 times negative 3 is 9, because minus minus makes a positive when you multiply, and minus 3 when you add them up, you get negative 6, so both check out. If you don't want to do this, you're welcome to do this factorization with the quad formula. For instance, you can actually figure out that the quad formula gives you certain roots, and you can factor it if it's factorizable with the quadratic formula's roots. Okay? Let's actually talk about this as another way to compute the find the zeros of this parabola, is to actually do something called completing the square and putting the equation in vertex form. So this is not so important insofar as the vertex form is important, but it's less important about finding zeros. Finding zeros in this course is mainly done through factorizing, if you can, or the bulletproof way is to use the quadratic formula. So let's actually see what happens. If you actually take this thing and set it equal to 0, you will get this thing. And you divide by a, which is not 0. You get this after rearranging. This thing can actually be 0 if k is 0, in which case we have a double root. If a and k have the same sign, then something squared is equal to something negative. Then this thing has no zeros. And if k and a have opposite signs, then something squared is equal to this little guy, which is positive, in which case we have two roots. That's just the three distinct cases of roots if you want to look at it through the lens of a vertex form. Again, not so important. You will need to know how to compute the vertex form of the formula, or completing the square the old school way, but you will not actually be expected to find the zeros using the vertex form. But if you want to, that's totally your choice. It's math after all, it's an exact science. So I don't want to go too much into detail like I did in class with this. In class, I should say, I didn't actually go into detail with completing the square and deriving the formula for the vertex form, because deriving formulas and proving things isn't the point of this class. What I will need you to know, you're welcome, of course, and encouraged to read this if you have time, but if you actually take a look at this, this is the vertex form of this parabola. And if you want to go from ax squared plus bx plus c, and if you want to go to this, then to go from this to this, you will need to do two things. Find the h and find the k. The a is the same for both of them. So this thing is the h, and this thing is the k. We have these formulas. So actually, insofar as using this vertex form, you will need to be able to use it and to figure out the vertex form of a parabola when you're given the standard form, meaning convert from this to this, courtesy of these little two guys right here. And if you actually want to take a look at what this vertex actually means geometrically, then the first of all, h comma k, meaning x equals h and y equals k, is actually on the parabola. Now, the vertex is in fact, depending on whether the parabola is smiling or frowning, that can either be the lowest point or the highest point on the parabola. So if you have a smiley-faced parabola like this, then this is the vertex, h comma k. That's the valley. If your parabola is sad, then it's this mountaintop, this peak, h comma k. You can actually investigate this geometrically. So that's basically what we mean by this, and you're welcome to read this little note to find the explanation. The explanation is that when you have x minus h squared, the least this thing can be is actually 0. So when this thing right here is actually x is equal to h in this thing is actually x minus h squared is actually going to be equal to 0. So in effect, when this thing is equal to 0, then the f of h is going to be equal to k. Good. Now, on the other hand, if a is positive, then a times x minus h squared is going to be positive. The least it's going to be is 0 when x is equal to h, because remember, something squared is going to be 0 or positive as long as you're not 0. That's why it represents the lowest point, like this, if a is positive. Whereas, on the other hand, if a is negative, then basically the a is going to penalize you. It's going to multiply. The a is going to multiply something negative, a times x minus h squared. So it's going to be negative times non-negative. So you're always going to end up with negative unless you end up with 0. In which case, the 0 will get you the highest possible value. That's for a is less than 0. Good. And this is in fact the relation, if you want to find actually the relation between the quad formula and the vertex formula. Again, not so important, this last bullet point. This one right here is not so important. But again, something you're encouraged to read if you have time. So let's take a look at this actually. Find the vertex form of f of x equals 3x squared minus 30x plus 76 and draw a rough sketch of its graph. Okay. Well, we're looking for, we have a equals this little guy 3, and we got this little guy negative 30, so b equals negative 30, and we got this little guy right here, c equals 76. Okay, so we have f of x is equal to a, which we already know, times x minus h squared plus k. Now let's go back to our formulas and write down the formulas for h and k. H is negative b over 2a. H is negative b over 2a. What is negative b? It's negative 30. So negative 30 divided by 2a. 2 times 3. So that is going to be plus 30 divided by 6, and that's going to be a 5. Good, that's your h. What about your k? Your k is going to amount to c minus b squared over 4a. C minus b squared over 4a. So that c is going to be 76 minus 30 squared divided by what? Divided by 4 times 3. Okay? So that is, if we simplify this, that's 76 minus 30 squared. Remember, minus squared makes a positive. Even powers kill the minus sign. So it's minus 900 divided by 4 times 3. If you actually cancel this, if you actually do this with a calculator, you won't find something that disgusting on an exam, but it's not that disgusting actually. You can do this. 3 divided by 900 makes 300, and this divided by this is 75. So you have 76 minus 75 makes a 1. So your k is 1 and your h is in fact equal to 5. So your f of x is actually going to equal 3 times x minus h, meaning x minus 5, squared, plus k, which is plus 1. And you can actually distribute the parentheses. If you don't believe me, you can actually distribute the parentheses to see that it is in fact the same parabola. This is the vertex form of f of x equals 3x squared minus 30x plus 76, which was originally given. And you're welcome to actually distribute the parentheses here if you'd like, to actually see that this is in fact equivalent to the old school given one. Okay, that's over and done with. Let's move on to properties of graphs, translations and reflections of a graph. So take, for instance, the concept of a vertical translation. If you have a function f of x and you know its graph, if you take f of x and add to that plus k, for instance, if you start out with x, and if you take x plus 3, then because I added the plus 3 to it, which is positive, I vertically shifted my graph 3 units upwards. Logically enough, if I were to do negative 3, then I will shift my graph 3 units downward. That's basically the way to shift the graph downward. This is what we call a vertical translation. You literally take your graph and shift it a number of vertical units up or down, depending on whether or not your k is positive or negative. Okay? If you actually take the graph and subtract h from the x that you're plugging into the function, then that's going to be that last one was a vertical translation. In this case, it's going to be a horizontal translation. So the translation is to the right if it's positive and to the left if it's negative. Let me actually show you something. Take, for instance, x squared. And if you actually take x minus 3 squared, then the purple one, the one that's shifted, is 3 units shifted to the right horizontally. Logically, if I do minus 3, which is minus 3, then it will shift to the left 3 units. That's the same as plus 3, by the way. Minus makes a plus. Okay, that's over and done with. That's what we mean by vertical and horizontal translations of graphs. And the next one, negative f of x, is the reflection of the graph of f of x across the x-axis. So take, for instance, x squared. And if you do negative x squared like this, then it's literally the reflection across the x-axis. You literally take the function and flip it over on its back. Good. And on the other hand, if you actually take f of negative x, then it's the reflection across the y-axis. Think even in odd functions. That's the reflection across the x-axis, and this is the reflection across the y-axis. Good. The last thing to talk about is the stretching and compressing of a graph. If you take a times f of x, that is a vertical stretch if a is greater than 1, or a compression if a is a fraction. So for instance, if a is equal to 2, logically you're stretching your graph by a factor of 2 vertically because a is multiplied by f of x. This might as well be called a times y. So if you're multiplying this by y and your a is going to be greater than 1, you're going to stretch this. 2 times y is twice the length of the original y, so it's a stretch. If, on the other hand, it's a fraction like half y, then it's a compression. Same thing for f of a times x, except that this is a horizontal compression if a is positive, if a is greater than 1, or a stretch if a is less than 1. Okay? Because this is a times x. The a is multiplying x. That's why it's a horizontal. Horizontal means x. Vertical means y. Good. Now, how do we graph the quadratic function in general? Well, let's say you bring it to vertex form, which is the standard practice for when you want to graph this, which every parabola can be brought to a vertex form. The idea is to start with y equals x squared, which is this parabola, which is as simple as can be. This thing like this, xy, that's this. Then you do x minus h squared, so you translate h units horizontally to the right or to the left, depending on the sign of the h. That's step 2. Step 3 means multiply by a to get this little guy right here in the vertex form. Good. That's step 3. And this is a stretch if it's greater than 1, or a compression if it's less than 1. Also, if it's negative, then you would need to reflect it. Remember, smile, happy versus sad. Remember, this versus this. This is what we mean by if A is negative. This is A positive and this is A negative. A positive means it's smiling, A negative, it's frowning. Then you add plus K. This is basically translating the graph vertically up or down depending on the sign of the K. So let's actually see how to figure out the graph of this little parabola right here. A equals -1/2. B equals 3. And C equals -5/2. Okay. Now the H is actually equal to -b/2a. So that's going to be -3 divided by 2 times -1/2. What is 2 times -1/2? It's going to be -1. So it's -3 divided by -1, which is 3. Awesome. And your K is going to be equal to C minus B squared over 4A. So that's going to be -5/2 minus B squared, so -3 squared, divided by 4A, 4 times -1/2. Now, in this case, what we have is -5/2 minus, this one is -2, so negative 9/2. So that's going to be -5/2 plus 9/2. That's going to be 4/2, and that's going to be a 2. So the parabola in vertex form is going to look like this. It's going to be, what do you get? A times -1/2 times x minus h, x minus 3 squared, plus 2, that's the k. Good. And so if you actually, you can actually expand the parentheses to see that this parabola is literally the original one given to you. We haven't changed anything, we've just presented it in vertex form per the formula. So -1/2 x squared and plus 3x minus 5/2. So if you actually take a look at this, then this parabola is frowning. And this parabola is actually frowning. If you actually take a look at it, let me fire up Desmos. It's going to be -x squared divided by 2 plus 3x, like this. And as you can see, the vertex is 3, 2. So that indeed checks out. The vertex is 3, 2. And you can also find the roots if you would like, but the point is that this thing is actually, the vertex here is actually 3, 2. 3, 2 is the vertex. Sorry, let me move down to the second page. 3, 2 is the vertex. In other words, if the graph looks like this, then that is indeed the 3, 2, the mountaintop, the peak. Okay, that's basically what we mean. You can also find the x-intercepts. So if you can see here, on Desmos, you can actually use the quad function or the vertex form, whichever you like, to actually find the roots. When you're given a plotting problem in this course, on an exam, for instance, there will always be instructions as to what you should pay attention to. Pay attention to roots, don't pay attention to roots, pay attention to even or odd, etc. So thank you so much for watching today, everyone. I will see you in class or in office hours soon. As always, if you have any questions or concerns, or if you would like to meet on Zoom for tutoring, just let me know, and I am happy to help you in any way that I can. Thank you so much.